So for this first problem, it's asking for the tension in cable AB and to determine all the reactions in the fixed support at D. So this is just one of our basic 3D reaction problems. First thing we're going to want to do is draw a free body diagram. Kind of looks like this. And there's some tension T here that connects to point B. And B is at 3, 0, 1. We can find that A is at 2, 2, 0. And we know that at D we have our dy and dx components. And we know we're also going to have an x, y, and z component of the moment about D. So the way I draw that is just by having some moment dx, moment dy, and moment dz. All right, make sure to also label where your x, y, and z components are. So from this, the first thing that I would do is to work on these reaction forces, dx, dy, and dz. And with that, we can just use our sum of the forces in each direction being equal to 0. So firstly, we have sum of forces in x is equal to dx plus this tension force over root 6. And the way that we got that was from finding our tension force in terms of a unit vector and its magnitude. So let me do that really quick. We have our tension T is equal to T UAB, which is equal to T times I hat minus 2J hat plus K hat. And we can get this just by subtracting A from B. And all of this is over 1 squared plus 2 squared plus 1 squared. And what that is and what that on the bottom is root 6, which is how we got that component being of root 6 for the sum of the forces in the x direction. For the sum of the forces in the y direction, we have dy minus 2t over root 6 equal to 0. So you can see that I'm just using our y component over the magnitude for this one, and for the previous one I used the x component over the magnitude, and for our sum of the forces in the z direction we're just going to have dz minus t over root 6 equal to 0. And you can see I'm using our z component over here over the magnitude. So what that is going to give us is our equations that we can solve for dx, dy, and dz, but only once once we plug in 24 kilonewtons for t, which is something that we're given in the original problem. So what we're going to get here is that dx is equal to negative 9.80 kilonewtons, dy is equal to 19.6 kilonewtons, and dz is equal to negative 9.80 kilonewtons. For our moments, what we have to do is have, our sum of the moments about d is equal to the moment at d plus our RDA, which is from here to here, crossed with the tension. So the way that we determine what that R is going to be is we want it from our point of reference, which is D, to where our tension begins, which is why it has to be specifically RDA rather than RAD. And what we're going to get from that is MD plus 2T over root 6 I hat minus 2T over root 6 J hat minus 6T over root 6 K hat. Okay. And all of this is going to be equal to 0. Solving this now, we know that each x, y, and z component has to cancel out with each of these components, which gives us that our moment dx is equal to negative 19.6 kilonewton meters. Moment dy is equal to 19.6 kilonewton meters. And our moment dz is equal to 58.8 kilonewton meters. So that is the entirety of the answer. I think that most importantly on an exam, you want to make sure that you have your correct moment equations and your correct force equations, because those are a component of the grade rather than just your final answer. So it's important to get those right so that you can at least get partial credit if your math is a little off. For the second question here, it's asking you to circle the two force members in each diagram, which is a really big part of a lot of the problems that a lot of the types of problems that we've been working on, including trusses, frames, and machines. So for the first one, I think my approach is usually to draw out what kind of reactions I have. And I know that each of these have matching reactions where you've got both an X and Y component because these are just pin joints. So I know that both of these members are going to be two force members. For the second one, same thing. These are all pin joints. So I know I've got these reaction forces at each of these joints, which means that EG and AC are both going to be two force members. Finally, here, it's really just the same exact thing. You know you're going to have an X and Y component of reaction force, making the entirety of AB also a two force member. All right, for part B, it says an object has a self-weight of 222 pounds acting on centroid C, and it's supported by two cables, a frictionless surface at A, and fixed support at B. Draw a free body diagram with all the forces and moments explicitly labeled. So this is going to get a little bit messy, but I'm just going to do it on this diagram here, though. If this were an exam, then I would recommend you draw another picture. So right here we know we have 222 pounds, as said, that is acting on point C. I'm going to go to A next. With A, we know that it's a frictionless surface, which means that it can move in your Y and X direction. So it's only really going to have a Z component going straight upwards. And it's also not going to have any moments there. So the same is not true for B, since that is a fixed support. At B, we're going to have a Z component, an X component, and a Y component. And then we're also going to have a component of moment for each X, Y, and Z. I'll do it in a different color so it's a little easier to see. So I'll call this my moment BY, my moment BX, and my moment BZ. So just remember, when you have a fixed support, you're going to have all 6 possible forces and moments acting at that point as a reaction. Going to point D, it says that those are 2 cables, and we know that with cables, the first thing we want to do is cut them. So I'm cutting at along those cables, meaning that I'm just really going to have these 2 forces acting in whatever direction is collinear to DE and DF. So here I'm going to have my TDE, and here TDF. All right, so that is all of our forces and moments. And you can see here that we have 6 unknown forces and 3 unknown moments. And that's just, 1, 2, 3, 4, 5, 6, and 1, 2, 3. Simple as that. So now for part C, we're asked to solve for the reactions at the fixed support A. So once again, we want to draw our free body diagram. We're told that this moment here is 600 pounds inches, and we're told that this force is 50 pounds. At this fixed support, we're going to have all 6 for forces and moments. So we're going to have a X, a Y, a Z, MAZ, MAY, and this is MAY, this was MAX. So firstly, we'll do our sum of forces in the X direction equal to 0, which is equal to F plus AX, giving us that AX is equal to negative 50 pounds. Sum of the forces in the Y is equal to just AY equal to 0, so we know that that's 0. Sum of forces in the Z direction is equal to just AZ, which is equal to 0, so we know that that's also 0. Now for our moment equation, we have the sum of the moment at A, I'm going to do at A, is equal to our moment reaction, which is going to be every component that we've already drawn at MA. So I'll just write that right now as our moment reaction, plus 600, which is from just the applied moment at the top. So I'll do 600 k hat because that is about the z-axis. And then plus our moment caused due to this force F. So that's going to be 0 I hat plus 0 j hat plus 12 k hat crossed with 50 I hat plus 0 j hat plus 0 k hat. And this is our R cross F. So if it's easier to see, you can write it like this with 0, 0, 12, and 50, 0, 0. And what this is going to give us is that our moment Rx is equal to, it's just going to be equal to 0 since there's going to be no I hat component at all. That's going to be 0, and our moment Ry is going to be, it's going to be negative 600 pound-inches, and that's because we're going to have 0 times 0 and then 12 times 50 over here. And remember that when you're doing the j hat component, it's minus this 0 minus 600 j hat. So what that is going to be is a positive 600 j hat, which we are then saying our sum of moment at A in the y direction is equal to MRY plus this 600 pound force, making MRY equal to negative 600. So hopefully that clears that up a little bit. And then for MRZ, it's also going to be negative 600 pound-inches, and there's going to be no component from this R cross F. It's just going to be 0, but since we do have this 600 applied moment, we know that it has to be negative 600 in order to counteract that. So these are our answers to that problem.
Okay, I'm gonna start with question 3. Here, you guys are gonna get the solution sheet later. So let's look at the problem. It says the assembly shown below is welded to collar A, which fits on the vertical pin aligned with the y-axis. The pin can exert couple about x and z axis, but does not prevent motion about or along the y-axis. For the loading shown, determine the tension in each cable and the reaction at A. Okay, so for any of these problems, first step is to draw the free body diagram. So let's do that. So in drawing the bar here and then C, and to expose all the forces that we need to solve for, I'm gonna cut at here at tensions and also A here. So we have A is told us that it exerts couple about A and Z, so it can move freely about the y-axis, so it wouldn't have a rotational reaction moment, and it wouldn't have force in the y, reaction force in the y, because it can move freely in the y. So then how we're going to draw this point at A is we're going to have a reaction in A, and then we're also going to have a reaction in Z, so AZ. And it also said that it can exert a moment about z and x, so we're gonna have the moment reaction here drawn in. I'm gonna draw in the positive direction because we don't know what direction it is in exactly, so we can just put it in positive for now. And then let me just define my, it's written up there, but I'm gonna z and x, so that's my coordinate. And then we also have the point D and C here, so we're gonna draw in those tangents. T, C, F. And that's a 800 Newton force. Okay, so for any of these problems, the first, after drawing the free body diagram, we kind of have to look at what you need to find. So we know that we have AZ, AX, TDE, TCF, and 2 moments. So that's more than 3 unknowns. So that means that we have to use the 6 equations method with the X, Y, and Z. So personally, how I like these problems is to first list out all the forces in their vector forms. So I'm going to write here, step 1. So we already know A, FA. We know that that is equal to xi plus k. So then let's look at TDE. So in order to find that, we need to find the unit vector so that we know which direction the force is going in. So how we can do that is to find the distance first. So that is just, we know it's RE minus RD. So that turns out to be 240J minus 180K in millimeters. And then from there, we can find the unit vector, which is 240J minus 180K divided by the magnitude, which is 240 squared plus 180 squared. And that comes out to be 0.8J minus 0.6K. So then that, from there, we have the first one, and then we can find TDE, that is just equal to the magnitude of TDE, multiplied by the unit vector, which is 0.8 J hat minus 0.6 K hat. Yep. And then we have TCF there. So same thing, let's find the distance. And that is equal to CF RF minus RC. And that comes out to be negative 160 I plus 120 J millimeters. And similarly, let's find a unit vector. And that comes out to be I hat plus 0.6 J hat. And then we find the vector form of TCF. So that's TCF I hat plus 0.6 J hat. And we have 3 forces there, so we know, and then we have one more. So that's this 800 here. I'm going to name it like F4 equals to, F equals to, and that's in the negative J height direction. So 800 J height. Any questions? Okay. So then we can move on to kind of next step. Okay, I'm gonna add a piece of paper. So after that, like we said before, we need to use our equation, and the purpose of finding the vector form is to make it that step easier. So we can do step 2. Sum of forces in different directions. So we have sum of forces in X equals 0, and we know from up here that we have AX we have this negative 0.8 TCF. So, and then that's it. So then we're going to move on to Y. And then we have 0.8 T DE plus 0.6, this one, TCF. And then we also have this negative 800. Ugh. Okay, and then we have one last one in the Z direction. So we have AZ direction, and we also have the negative 6K there. So 0.6 TDE. Okay, so then after we found this, we can tell that none of these you can't really solve. There's like 4 unknowns, so you can't really solve using just these. So we're gonna move on to the moment, and then come back to this later. Some moments. Give me 1 second, I have to charge my laptop. And by the way, these are recorded, so you can see it later. We're gonna post it. The problems that we're going through. Okay. So that's some moments. So you can pick whatever point, but honestly, obviously the easiest point is gonna be A because there's the most forces there. So we're gonna do moment about A equals 0. So then we know that there is. I'm gonna move this over here. Okay. So we know that there is, from just the reactions, MRZ, and this is in all directions. This MA here is in all directions right now. MAZ plus MRX, and then we have this is going to create a moment, this is going to create a moment, and this is going to create a moment. So we're going to have to use those 3, 2. And in this problem, I'm going to use the vector method. On the solution that's going to be posted later, it's going to have the scalar method, but I personally find the vector method a little easier to do. It might take a little longer, but like it lays out things more clearly in my personal opinion. So that's what I'm going to do, and also just to show you guys like a different method to do it. So then we have plus, that goes from A to D, so RAD, cross TDE, plus RAC, and cross TCF, and we have one more here with the 800, so that's also RAC, cross 800. I'm gonna put a F, cross F. Okay. So we can do these each individually, but to make this a little easier, let's solve for RAD and RAC first. So we have RAD is equal to RD minus RA. So that's just equal to 160 I hat plus 180 K hat millimeters. We have RAC, similarly RC minus RA, and that's gonna be 160 I hat plus 270 K hat millimeters. So let's start with this one here. So let's say 1, we'll have RAD cross TDE, and we're gonna use the determinant matrix thingy. So that's gonna be I, J, and we have K. So let's use, we know for RAD, we have I hat 0 and 180 in the K hat direction. And then for TDE, which we have up here, we have 0.8 TDE and negative 0.6 TDE in the K. So that's going to be 0.8 TDE and then negative 0.6 TDE. Okay, and then we can solve for this matrix. So multiplying these two first in the I hat. So that's 0 minus 180 times 0.8 TDE. Okay. And that's an I hat. And then we have J hat. J hat, so we're gonna cross these outer ones. So that's gonna be minus 160 times negative 0.6 TDE, J hat. And then we have one more in the K hat, so then that's plus 160 times 0.8 TDE. That's in the K hat direction. And then we can sum those, kind of just simplify those. 144 TDE. And then we have plus 96 TDE, J hat, plus 128 TDE, K hat. And that's in Newton millimeters. So that's the first one. Let's go on to the second one with the RAC cross TCF. Same thing, let's do the determinant. I, J, K. From A, RAC, we have 160I, 0J, and 270K. And then we gotta look at TCF, which again we did up here, this one. So we have negative 0.8I, and 0.6J. TCF. Okay, same thing. Let's do a cross product. So we have 0 minus 270 times 0.6 TCF I hat minus 0 minus 270 times negative 0.8 TCF J hat. And then we have plus K hat, we have 160 times 0.6 TCF minus 0. So K hat, and then let's simplify that again. We have negative 160 to TCF I hat, 216 TCF J hat. We have 96 TCF K hat, Newton millimeters. Okay, one last one. 3. RAC cross F. And that's I, J, K. Have up here 160, 0 to 70. And like we said before, it's going to be negative 800 J hat. So that comes out to be negative 0 minus 270 times negative 800. That's an I hat. And then j hat we have 0, so then let's move on to k hat. We have plus 160 times negative 800 k hat. Okay, so multiply that out. That is 216,000 I hat minus 128,000 k hat millimeters. Okay, now that we have all of the component form of the moments, we can sum all the moments. So we do sum moment, and x is equal to 0, and we know that the first one we have MRX, reaction moment in x at 0.8, and then we have this one up here, and this one up here, and this one up here. So we can do plus 216,000 minus 162 TCF minus 144 TDE. Okay, so that's x. Then go on to y. Y, remember, there's no reaction moment, so we're not going to include that. And then we see that there's one here, and there's another one here. Let's write it down. Negative 216 TCF plus 96 TDE. Okay, one more. M in the z direction. So that is, we have our reaction, so RZ. And then we have this negative big number, and then that, and we also have that. Okay, so we're gonna write it down. 128,000 plus 96 TCF plus 128 TDE. Okay, so now we have all the equations. You can see how there's 1, 2, 3, 4 equations here again. So it looks kind of unsolvable. But if we kind of look at this equation here, there's 2 unknowns. And we can look back up to the sum of the forces we put up here. There's also the same 2 unknowns in this equation. So what we can do is kind of find a ratio, solve for one in terms of the other, and then plug it back into the top. So let's do that here. So we can say TDE is equal to 216 TCF over 96. And then that's just 2.25 TCF. Okay, so we're going to plug it in back to the top. So here, I'm going to have, I'm going to remove this. We can move the 800 to the other side. 800 equals to 0.8, and we solve for TDE. So we're going to plug in TDE is 2.25 TCF and plus 0.6 TCF. So now we can solve for TCF. And we're going to find that its magnitude is going to be around that value. So that's our first one. And then we can plug that back into the y to find TDE. And that comes out to be 750 newtons. And then similarly, plugging it back in, we find that AX is going to equal to 267 newtons. And AY is, AZ is 450 newtons. So we found all the forces. Let's go back down to solve for the moments. So we note both of these. So we're gonna find that MRX is equals equal to 0, actually. Oh, no, that's MRZ, sorry. So negative 54000 Newton times millimeters. And MRZ here is gonna be 0. Okay. So then we can also put that in meters. So because this is the only reaction moment, you can say that the MA, the reaction A at A in total is just negative 45 Newton meters. Okay. So I think that's it for this question. Any questions?
Okay, so question 4 looks deceptively challenging, but hopefully this will clarify it a bit. It's asking you to determine the reactions at A where the wing is fixed. So we know that A is a fixed support where we have some AZ, some AY, some AX, and some moment X, moment Y, and moment Z component. We also know from the problem that at point G we have some 2.1 times 10 to the power of 3 kilogram force, and that our thrust force and L is 45 kilonewtons. That's our lift force. And it also gives us the dimensions of A, B, C, and D. So instead of, getting too bogged down just like looking at this question, I would just start right away with solving our sum of forces in the X, Y, and Z direction equations, because that's going to be the easier part. It's going to allow us to just, visualize what we're working with a little bit better. So starting out, we have our sum of the forces in the X direction equal to 0, and this is just going to be negative AX plus T. And since we know what T is, just 8 kilonewtons, we know that AX is equal to 8 kilonewtons. Moving on to the sum of the forces in the Y direction, we have actually only AY going in this direction along the y-axis. So we know that AY is just going to be 0 kilonewtons. For some of the forces in the Z direction, we have that negative AZ minus this mass that we're given, which is 2.1 times 10 to the power of 3. And then don't forget to multiply that by G, so multiply that by 9.8, plus that 45 kilonewtons from the lift force. And what this is going to give us is that AZ is equal to L minus 2.1 times 10 to the power of 3 times 9.8. And AZ is equal to 24.4 kilonewtons. So moving on to our moment equations, it's actually not too difficult to do this with scalar method, although usually I would suggest using vector method to solve for your moments in a 3D problem, but just in the interest of showing you how you could possibly accomplish this, we can do our sum of the moment about y equal to 0, and this is just going to be our moment y. Here, I'll call it moment ay. Throw an a in all of these just to make it a little bit more distinct from, our sum of the moment in the y. Equal to 0. And I'm doing all of these about point A. So we'll say this is our sum of moment in the y at A. And that's going to be MAY minus that thrust T times our distance. You can't really see it now, or it's a little difficult to see, but our distance A. And that's going to be equal to 0. So you get that MAY is equal to 20.0 kilonewton meters. And the reason that we're just using that tension T is because the weight at G and our lift are not going to produce moments about the y-axis since they're acting directly on the y-axis. Only T is going to generate a moment that goes around the y-axis. Moving on to our moment at x equal to 0. And we're going to do that at A. This is going to be our lift times B plus C plus D, because that's, the full total distance there, minus the weight, so 2.1 times 10 to the power of 3 times 9.8 times B, which is the distance in the y direction, minus mx. And the reason that we're using, the distances that we did is because those are what is perpendicular distance from where A is, respective to finding the moment about the x-axis. So from this, we're going to get that mx is equal to 572 kilonewton meters. And then for the sum of the moment about Z, also at A, we're going to get mz minus just the tension times B plus C. So you can see that something that I like to highlight is that for finding our moment at Y, we use this vertical distance, A, but for finding it at Z, we use BC. And that all has to do with which axis we're finding the moment about. So always keep that in mind. If you're using the scalar method, you have to be very cautious about the distances that you're using, because it's not just like any perpendicular distance will work. It has to be, with respect to the axis that you're thinking about, because A is the perpendicular distance from Y, whereas BC is the perpendicular distance from the Z axis. Okay, so this is equal to 0, which gives us that mz is equal to 64.0 kilonewton meters. So that's the entirety of this problem. Those are all your answers.
So let's move on to the next problem. I'm gonna go for problem 6 here. Okay, so find the reaction at A and D, as well as the force acting in each member of the truss. So we're gonna have to do some sort of truss joint analysis, and then B, which members might buckle. Okay, we can come back to these later. So let's solve for A first. So for any of these truss analysis problems, the first step is always to analyze the whole truss in order to find these reactions. So free body diagram of entire truss. We have shallow framing. Okay. So A here is a roller support. So what we know about that is that it still can move freely in the, I'm gonna define this to be X and Y. So it can still move freely in the X direction. So it will only have a reaction force in the Y direction. So we're gonna put that in, we have AY. But D here is a pin support, so we're gonna have the X and Y because it cannot move freely in any of those directions. So dy and dx. And then let's put in the applied forces. So we have a 3 kilonewton and a 3 kilonewton. Okay, so let's find the AY, dy, and dx by summing the forces. So we can say sum of forces in x equals 0 equal dx. So that means that dx is just equal to 0. And then we have sum of forces in y equals 0. We have ay minus 3 kilonewtons. I'm going to say 3. Minus 3 plus dy. Okay, then we can't really solve for that yet because there's two unknowns. So we're going to use the moment equation. I'm going to do it. It doesn't matter what point you pick, so I'm going to do it from A. So from A, we have 3, and this distance is 3 kilonewtons times 3 meters. This is using scalar method. So, and it's gonna go clockwise. So that is the negative direction. So negative 3 times 3. Similarly, this is 3 plus 6, so 9. And it's also gonna be clockwise, so negative 3 times 9. And we have dy. That is gonna go in the clockwise direction, counterclockwise direction, so that is positive. And that distance is 12 meters. So we can solve for dy. And that's gonna be 3 kilonewtons. And we know from there, plugging back into this, ay is also gonna be 3 kilonewtons. Okay. So from there, we can pick a joint, like to find the forces in each member. We can pick like whatever joint, right? And then find the force from there. But the easiest ones are obviously going to be A and D because we already solved for the reaction moments there. So it's going to make it easier because if you pick like a random point from D, you don't know any of the forces. So it's going to be kind of useless in the sense that you can't solve for anything yet. So let's start from joint at A. So 1 up to A. Okay, so let's do just a join in. We know that there's an AY, and that's gonna be equal to 3 kilonewtons. Yep. And we know that's the right direction because the answer came out to be positive. So I'm gonna draw in that direction too. And then we have F. I'm just gonna say AF, and then we have AB. And then that angle, I'm gonna name it alpha right here, is going to be equal to, we have this distance here and distance here, so 10 of 4 over 3. And that's just 53.1 degrees. So we can use that when we're summing the forces. X equals to 0 equals to, we have just AF here and the horizontal component of AB. So we have AF plus AB cosine of 53.1. And then sum of the forces in Y, we have 3, which is AY here, and then plus the vertical component of AB. So then we can solve for AB, and that's equal to negative 3.75 kilonewtons. And then plug it back into sum of AX. So we find that AF is equal to 2.25 kilonewtons. So the negative answer of AB tells me that this thing here, which I assume to be in this direction, is actually in this direction. And I'm just saying that because it will be useful later. So let's just keep that in mind. So then we can pick another joint. So we did A here, so I'm gonna go over to D. We can also do like B or F, but I think it'll be easier to start on the two sides. So let's do D. So we have a dy, like we said before, which is gonna be 3 kilonewtons. And then we have a dc and de. So I'm also gonna assume dc and de. And this angle again is going to be this alpha thing I defined. So let's sum the forces again. 0 equals to, we have a negative dE going in this direction, so negative dE. And then we have the horizontal component of dE, so that's going to be cosine of 53.1. And then we have the sum of forces in Y. We have 3, and then also the vertical component of DC. So let's add, oh wait, I did the wrong thing here. It's DC. Okay, DC sine of 53.1. Okay, so then similarly we can solve for DC, and that's going to be equal to negative 3.75 kilonewtons. Plugging it back in, we get that DE is equal to 2.25 kilonewtons. Okay, so we can move on from here. I'm gonna pick, we already know this, so I'm gonna pick C, because we know one of the forces, so there's only gonna be 2 unknowns at C over there. So let's do, I'm gonna move this up here. 4, pin at C. So then we have, okay, so when I said before, like, negative signs means that it's just going the opposite direction. So this means that this is actually going in this direction. And for a member, the forces are either gonna both come out, which is gonna be compression, or they're both gonna go in. So in that case, we know that this is actually the correct direction. That means that for CD here, we have D and C, it's going there, so then over at C, it has to be that way. You can draw it in whatever direction, but I like to, I like to build onto each of the fruit body diagrams. So using that information, we know that C here is actually gonna go up. So DC, and we solved for it before, is going to be 3.75. So you don't have to worry about putting a negative or positive here, because we already labeled that to be the direction that's going in. Nuance. And then we have a CE and CB. So that we don't know what directions they're going in, so I'm gonna put a random direction, and we're gonna find out later if it's right or wrong. So BC. And that angle again is going to be alpha. Okay, so let's sum the forces. Fx 0 equals to, we have BC here going into the positive direction, and then we also have the horizontal component of DC, but that's going to be negative. So minus, oh actually we can just write down the value. I like to write in the value sometimes because I might forget that I already solved for it if I didn't write it down. So then it's easier to keep track of, so to know that I actually don't have that many unknowns and I can actually solve for it. So 2.25 kilonewtons. So that means that it's the right, I drew BC in the right direction. and then we have sum of forces in Y. Let's move this up. And we have CE plus DC, 3.75 sine of 53.1. So we get that this CE is equal to negative 3 kilonewtons. So again, wrong direction. That's okay? Okay, so then from there, we can move to each of the joints. Move to the joint that kind of is close to the one you already solved for. So you already know some of the forces that exist. So I'm going to go to E here because 1, 2, 3, 4. Actually, yeah, I'm going to go to E here. You can pick which one. Okay, so we already know the E, and we get that D up here is the right direction. So that means on the other side, it's going to go that direction. So DE, and that's equal to 2.25 kilonewtons. And then we also solve for CE here. And then we got that it is in the wrong direction. So that means that C is actually going this direction. So that means this member is in tension. So this force is also going to go up. So we get CE is equal to 3 kilonewtons. And then we have 2 more members and an applied force. So we don't know which direction those are going, so we're going to say 3 kilonewtons applied force there. And then label whatever direction. We have EF, and we also have EB. And that angle, we don't know which angle that is. We're going to say that's theta. So theta. Okay, I just kept going, but any questions so far? We're good? Okay, I'm gonna keep going. So then sum of the forces, we have X 0 equal to negative EB. We have cosine of theta plus DE. DE you already know, so 2.25. Okay. And then we also have a EF. Okay. 0 equal to, we have CE minus 3. Oh, C already know, that's going to be 3. 3 minus 3, that's going to be 0. So then we also have EB here, which is going to be plus EB sine of theta. So because this is 0, we know that EB sine theta is equal to 0. So that means that EB is actually going to be equal to 0. And then plugging it back in, we know that EF is going to be negative 2.25 kilonewtons. Okay. So we have this one, 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 this one. So we just have this one left. So we can either do the point at B or F. So I'm gonna pick F. Yeah, okay. Okay, so 6, I'm gonna do F. So there is applied force going down 3 kilonewtons. We have from the previous one, we have EF, but again, that's going the wrong direction. So that means that it's actually this direction. So that means that the member itself is in tension. So I'm gonna draw it here in tension as well. So going this way, we have EF equal to 2.25 kilonewtons. And then we have BF, and we also have AF from this part. So AF up here, we have it in the right direction. So that means that the member itself is in tension. So let's draw this in tension as well. So AF, and that's equal to 2.25 kilonewtons. So summing the forces, we only really need to sum the Y. So let's just sum the Y because we already know the two sides, and that's BF is the only thing we're solving for. So BF minus 3. So BF is just going to be 3 kilonewtons. Okay, so that's part A of that. Let's go on to the second part B. So it says which member might buckle and which member could be replaced by cables. So when it says which members might buckle, you guys might do this. I don't know have you guys already done it in like the truss design? Okay, doesn't matter. So when it says which member might buckle, we're just looking at whatever member that has the most force that it has to be holding. So if we go down to all the answers, we can see that AB here has the most forces and DC also has the most forces, which means that AB and DC here are gonna buckle. But if we think about this kind of physically, right? If these two bend somehow, right? So this goes down, and these two like bend somehow, it can't just bend by itself because the whole system will have to kind of go down together, I guess. So then that means that this member up here is also gonna buckle, probably like that. So that means that, when I ask which member might buckle, we have AB, DC, and also BC. So then we have which member could be replaced by cables. So what we know about cables is that it's like a string, it can only pull anything, so that means that, so let's draw it, right? So if I have a cable, so it can only pull in. So what this means that this is similar to a member in tension. So that means that we're going to look at each of these and see if they're in tension or compression. So let's look at AB. So like I said before, if it's in tension, it's gonna, so this is one joint, this is the other joint, right? So it's gonna have to kind of go. If it goes into the joint, it's in tension. If it goes out of the joint, it's in compression. This is tension, and this is compression. So AB here, it's in the wrong direction. So that means that it's in this direction. That means that it's going into the joint. So this is in tension. Let's highlight that. And then AF here is going out and it's the right direction. So this is this is also right. Yeah, this is compression, sorry. Wait, JK, I'm doing this wrong. I'm sorry, I apologize. Okay, so when you have two joints here, if it's going in this way, it's tension. And if it's going out of the joint, that's compression. Yes. So then AB here is it's pushing down because this is the member here. So then that means that it's coming out this way, so it will be in compression, not tension. So compression. Okay. And then we have AF here. It is going, this is the member. So it's going inside of the member, so that's going to be in tension. So let's add that. Okay, let's go down to this. We have DC, like I said, it's the wrong direction. So it's going into the joint. So it's gonna go out the member. So that's gonna be compression. And then DE here is going into the member. So that's gonna be tension. Let's highlight all the tensions. And then let's go into BC here. BC that's the right direction, and it's going into the joint, so pulling out of, so it's exerting the force on the joint instead of going to the force. So compression, and then this is C, wrong direction, so it's going down this way into the member, so that's going to be tension. Okay, so then this one is a zero force member because it doesn't have any force exerted on the member. And then EF here is wrong direction again, so then it's going into the member, out of the joint, so that is going to be tension. And then similarly going into the member, out of the joint, so that's going to be in tension. So anything that's in tension can be replaced by cables. So that means that there is AF, BE, CE, EF, and BF. Okay. Last questions, any zero force members? We can already answer that. That's only going to be EB down here because it doesn't have any force. That's it. Any questions?
Okay, so for this question, it's a little bit of a complicated situation, but let's work through it together and break it down, and hopefully it won't be that bad. What's really great is that they have kindly given us this free body diagram, which is going to be really helpful since it's a little difficult to draw out what we actually have here. And the first thing that I want to do is identify where each of our points are, A, B, C, D, and F, just because we're going to be needing to find a lot of R vectors, distance vectors or direction vectors, and it's really helpful to have those all laid out already. So starting with A is at 0 to 4.5. B is at 3 to 4.5, C at 3, 1, 4.5, D is at 3, 1, 0, and F at 2 to 4.5. I'm already finding this a little bit easier to visualize because it just kind of confirms for my mind that A, B, C, and F are all at the same z distance away from the x-axis, which makes this whole problem just make a little bit more sense to me. So next thing I'm going to want to do is, using this information that the pipe weighs 0.85 pounds per feet, I want to find the weight of our different members here. So I know my weight AB is going to be negative 0.85 times the length of it, which is 3 feet. And we can tell this by our coordinate system here, where we got 0 and 3, so we know it's 3 feet long. It said that it's 0.85 pounds per feet, and what that's going to give us is that it's equal to negative 2.55 pounds. And that is in the negative j hat direction. So that is that WAB. Moving on to WBC, the exact same method, but BC we can see is only 1 foot long, so WBC is just going to be negative 0.85 pounds in the j hat direction. That's that one. Next, WCD is going to be equal to negative 0.85 times 4.5, which is how long CD is. We can see from our 4.5 and 0 here. And that's going to be equal to negative 3.825 in the j hat direction. All right, so we already have those 3 unknowns. And the next thing that I'm going to want to solve for is this tension here. So following our, original method, we did on midterm 1 even, of solving for our tensions and forces, we're just going to find the magnitude multiplied by the unit vector. And we're going to want the unit vector from point F to point E. And what that is just going to be from, we're going to designate the origin as point E. Or, excuse me, not the origin, what we have up here, from F to E up here. And what we're going to get from that, also, I should put in where E is. E is at 0, what's that height? 0, 5, 0. Alrighty. So given that now, we can do our unit vector from F to E. And what that's going to be equal to is our tension times negative 2I hat plus 3J hat minus 4.5 K hat. And that's taking E subtracted from F. Or, excuse me, that's taking F subtracted from E. And all of this is going to be over root of 33.25. You'll have to take my word on that. That is 2 squared, 3 squared, and 4.5 squared added. Something else that's going to come in handy is finding the unit vector from A to D. So I'm just going to do that really quick. What that's going to be equal to is 3I hat minus J hat minus 4.5 K hat over root of 30.25. So we know that all of these weights are at the midpoints of each of their respective members. So that's something good to keep in mind. Where we're going to next work with our moment equations to try to solve for what our tension actually is, this magnitude here. So first of all, I'm going to do, I'm going to shrink this down a bit so I have a little bit more room to work with. And we're going to take the moment AD equal to 0, which is why I found that unit vector. And this is equal to the sum of the moments about A times that unit vector AD. So this is a concept that we learned a while ago, where you're finding the moment about an axis that is not just the x, y, or z axis. So in this case, we're finding it about the AD axis. And the way we're doing that is just finding a moment along that line and then dotting it with the unit vector of that line. So that's going back to some concepts we learned at the very beginning of like this kind of what this midterm is covering. And what this is going to be is going to end up being a big long moment equation. So I'll just write that out, where we have RAF, so that's A to F here, RAF crossed with the tension T there, to find that the moment that T is generating, plus 1.5 I hat times WAB, and that is going to be the moment that WAB is generating, plus 3 I hat crossed with, or I'm sorry, this is also crossed with WBC, which is the moment that WBC is generating about A, plus 3 I hat minus 2.25 K hat crossed with WCD, which is the moment that WCD is generating. So the reason we have 3 I hat minus 2.25 K hat is just finding that R vector from A to where WCD is taking place, which is at the midpoint of C and D. And then we're also going to want to add our RAD crossed with our DY and DX or DZ components here, which is important because those are also both contributing to a moment about A. And then this entire thing is going to be dotted with our UAD, but I'm just going to solve this out first. So what we're going to end up getting here is 6K hat plus 9J hat times tension over root of 33.25 minus 1.5 times 2.55 K hat minus 3 times 0.85 K hat minus 3 times 3.825 K hat minus 2.25 times 3.825 I hat. And what that's going to be is we're going to eventually end up getting we're going to end up multiplying this by UAD, so I'm going to do that right now. Here, we'll put this in red just to make it a little bit easier to see on here. So this whole thing is my moment component, and we're going to dot that with my UAD component here. Maybe we'll put it all on one line to read it better. We're going to dot that with 3 I hat minus J hat minus 4.5 K hat over root 30.25. And all of this, it has to be equal to 0. And you remember that what we have here is the same as what we calculated up here. So, solving this out a little bit more, we'll get 6t now over root of 33.25 minus 3.825 minus 2.55 minus 11.475. All of this multiplied by negative 4.5 over root of 30.25. And then adding this to 9t over root of 33.25 times negative 1 over root of 30.25 plus negative 8.606 times 3 over root of 30.25. All is equal to 0. So what we're doing here is we're doing our typical, dot product where we're multiplying the x, y, and z components within their own families respectively, and then adding them together. And what we're going to end up getting from this is, I'll simplify it down a little bit more, negative 4.5 times 6t over root of 33.25 minus 9t plus 80.325 minus 25.98. And this will allow us to solve for this t term that we have here. Oh, this is all equal to 0. In solving for that t term, we are going to get that t is equal to 8.70 pounds. So we're going to stop here because we're only asked to find what that t is. But this can be a kind of confusing problem just because we have so many different forces. I would say more than being able to do all of this stuff, the most important thing is being able to set up this moment equation where how each of these forces are going to contribute to a moment about A, and you're doing R cross F for each and every single force. Remember that your R vector is going from your reference point to where each force is starting. So I'll draw them all out here. My R vector here, my R vector to the tension, my R vector this way, my R vector to this way, and my R vector to these reaction forces. They should each be coming from A and pointing towards wherever those forces are acting, which is a really, really common mistake to make because then it just, flips what the moment you solve is. It inverts it, gives it the wrong signs. So it's really important to make sure that all of your R vectors are correct. That is the general idea of how to solve this problem. Thank you for bearing with me through it.
Okay. So the first problem says that P equals 800 pounds and we need to find the force in each of the member of the truss and then state if the members are in tension or compression. So this is a truss problem, right? What would you guys do first for any truss problems? Any volunteers? Yes. The body diagram of the whole thing. Do we have any other suggestions? Okay, so why do we draw the free body diagram of the whole structure? for the reaction. Yes, but when you do that, like what type of forces are we solving for? Those are like the external, right? Okay, and then for this problem, what is the external forces? Yes, so that's very important to realize first, right? Because when you draw your free body diagram later, when you break it up, you don't want to miss those forces, right? So let's do that really quickly. It doesn't really matter which direction you define it as long as you stay consistent with your free body diagram, then it's fine. So I'm just gonna say something like this. Arbitrarily, this is gonna be our forces. And to make this problem a little easier for ourselves, we can simplify it, right? And the first step we could do to simplify is identifying the zero force members. Do you guys see any zero force member just by looking at the structure as a whole? Sorry? D? D and E? Or is that what you're saying? E and B? That's correct. So this is gonna be gone. Anything else? Give you guys a hint, there's one more. Okay, I'll just tell you guys. It's going to be C and D. Does anyone have questions about the 2 zero force members? Okay. Then next, what we want to do is solve each of the joints. So we can start at joint A. So let's draw out this part as a free body diagram. We have an external force P. And then we're gonna have the force A and F. And we can break up A and F into a X component and a Y component, so it's easier for us to solve later. And we will also get a force here. And this is going to be FAB. Does anyone have questions? Yes.
What does it mean by zero?
A zero force member. So if you, let's look at this one, E and B, right? If you draw out the free body diagram, let's say we're analyzing the structure at E, right? So what forces are present here?
Oh,
Do you want to tell me?
yeah, the force is at.
Yeah, it's just like, if you look at the structure, you see there's a E and D force, right? And then we also have the F and E force, like that. And this is gonna be the EB force, right? And if you do your equilibrium equations, you have f of x, sorry, this is EF, plus, you have ED, and that's going to be 0, which you could solve for. But notice for the force of y, there's nothing except force EB that contribute to a y component, right? So if you write that out, you'll notice that it's just going to be 0, and that can make our lives easier, and we can just cross that out. Yeah. This is just one example. And then we also have forces that kind of look like that. But for this one, basically it's the same idea. It's like when you do your sum of forces in X, sum of forces in Y, you'll notice that this part is the only one contributing to a Y force, or like an X force, and so it's just gonna be 0. Oops. Okay. Good questions. Let's keep going. So now we write our equilibrium equation. So since we already defined our x and y component of force AF, that makes it a lot easier for us to write out your equilibrium equations. So solving for these equations are not hard. It's just very simple algebra. But I think an important thing to keep in mind is drawing the correct free body diagram, recognizing the x and y component forces and the angle. It's very important in some of the later problems that we're going to look at. Alright, so now let's move on to another joint. I'm just going to pick joint F. You could do whichever one you like. But if we look at joint F, well, actually, we have to do joint F because it's just easier after solving for FAF and the force AB. So we're looking at this one. And let's draw a free body diagram. This is going to be F. This is going to be E. We have an external force of 500 pounds here. We have a force FE going like that. And we also have an angled force FB. So first thing I would do is break up FB into x and y components. Could do it like that. And we know this is going to be 45 degrees. And let's bring that down. Does anyone have questions about the free body diagram? Alright, now we're gonna write out our equilibrium equation. This is the easy part, so I'm just gonna kind of write it out for you guys. So solving this equation, we will get Does everyone see how we got to this equation? Alright, now let's do the x component. Forces contributing to the x component, we have Fe, and this is going to be Fb, the angled force. Sorry, this is Fb, I said solving this equation, this is the solution. Does anyone have questions? Alright, now we're going to move on to the next joint, which is joint E. We draw out the free body diagram. There's going to be a force ED and a force FE. And we don't draw EB because we found that's going to be 0. So it wouldn't really help us. And if we write out the equation, we see that the force Fe is going to equal ED, because they're equal and opposites, and so we can say that ED is also going to be 2,010 pounds. Alright, the last part that we need to analyze is this joint right here. So this is going to be joint E. So in our free body diagram, we have force BD going like that at an angle. We have this component. We have FB, AB. And like we mentioned before, we cannot forget about this force right here. So let's just write it out in a little clearer way. We can break this up into X and Y components. This just means like the normal force at C. And then we know that AB is 800. So now solving for this free body diagram, we have BD contributing to the Y force, and we also have FB contributing a y force. And from this equation, we get a value for BD. Does anyone have questions? All right. So now we're going to do the same thing for the x forces, plugging in all the values that we know. We can find that BC is going to be this value right here. So now if we start looking at all the forces that we found, we can make a conclusion that at joint C, the sum of forces X will give you the normal force at C, which we kind of accounted for when we drew the free body diagram for joint B, and that makes sense. Any questions? All right, let's move on to the next problem. So this is another truss problem, which means we need to look at all the joints and analyze them one by one. So plugging in what we know, this is going to be 240 pounds and 100 pounds. And with this problem, you're not given any angles, so we really have to utilize the triangles. So let's draw out our free body diagram. We always start with a free body diagram. Actually, even before we draw a free body diagram, how do we simplify this problem? So same thing as we did before, we always want to identify the zero force members. Can anyone tell me which force we can just kind of cancel out? Because it's just going to be zero. Does anyone have a suggestion? All right, I'll just tell you guys. The zero force members are here. Does everyone see that? All right, so now we can draw a free body diagram, and it will be a lot easier for us. So instead of drawing the whole thing like we were going to do, now we can simplify it to just this triangle right here, because we know everything else is going to be zero. So this is going to be joint C, D, and B. We have a gonna be P1, P2, which is what the problem gives you. And now to simplify a little further, what else do you guys recognize from this free body diagram? What forces do we see? Any suggestions? Alright, from here we can actually identify that force BD will look like this. And then for C, since we have a pin support, we're going to have our normal to CY and CX. And let's make this even more clear for us. Let's add in the dimensions, so when we solve for our equilibrium equations later, it'll be very clear. So for C equals 12 squared, 5 squared, just a right triangle, and we get 13 feet. Do we have any questions so far? All right. Now we can analyze joint by joint. I'm going to choose to do joint D first. And this is going to be our equilibrium equations. And just plugging in the different forces that contribute to Y and X, we're going to get BD 5 over 13 minus 100. And we get this by using dimensions of the triangle instead of the angle, because we're not given that. So from this equation we get BD is going to be 260 and is in compression. And we do the same thing for the X component. We have 240 CD 260 that we found earlier. And this is what we're gonna get for CD. So that's all we can find at joint D, and we move on to another joint. So the third step, we're gonna look at joint B. And we can do the Y component. And now we're done with the problem. So just to summarize truss problems in general, what you always want to do first is simplify. So identify the zero force member. This way, it kind of simplifies your free body diagram, eliminates a lot of mistakes. So always do that for truss problems. And then you want to identify your other forces, such as two force members. And by doing just these two steps, you're going to get a free body diagram that's a lot more manageable. Then we look at each joint and solve your equilibrium equation. So that's just going to be sum of x equals 0, sum of y equals 0. And you guys have been doing that since the beginning, almost. So we're good. Yes?
So how can you determine if a is just a two-force member?
Sorry?
How can you just determine BD is
BD here?
yeah.
Because, well, if you... Do you see how... Basically here and here, just imagine that they're pins, right? What you can do is you can kind of unscrew it and then take out B and D literally. So when you take it out, it's just like that, right? So then you have a BX force, BY force.
But I thought you usually BY stands for a roller or something on the y-axis. Based on the setup.
Is there an error with the answer key? The answer key said B is BY, BX, which is what I did, because that's the only way you can solve for all the forces.
Yeah.
But B is a roller.
Yeah, so there's no BY.
But then how do you use the two forces? BD. But then you can't
You
solve.
can still use it. There's a BX and there's a BD.
Okay.
I think
You sure?
I think so. Nothing wrong with this.
It was like that.
Well, there wouldn't be a BY, isn't there?
That's what I thought. Actually, yeah, you're right, because we're only using the FY.
I think only using
Oh,
BY.
FX. Yeah, why is there a BY? You know what, we're gonna come back to this problem.
Should I go with BC? Is that what that is?
This one? And this is
Like this.
Did anyone solve this problem? You did? Okay, what was 260 for you?
I think I got the same thing.
You got the same thing?
Yeah. And like I didn't assume this was a two force member. Like I
Uh-huh.
solved and I got that that was a zero force member.
Oh. Yeah, we got the same thing.
Yeah.
We'll come back to this problem. Alright, let's just move on. But we'll come back to this. Okay. Now for this problem, we're going to use the same 3 steps. So we need to identify the zero force member, other forces, and then look at each joint. Does anyone see zero force members in this problem? So we don't have any zero force member, right? So we can go straight into analyzing each joint. So I'm going to start with joint A. we see there's a P force, AF force, and an AB force. I'm just going to draw it this way, but direction of the arrow does not matter. And by looking at the structure as a whole, we see that this is going to be 45 degrees, like so. So now that, yes? Sorry? 45 degrees. If we draw it out, this is going to be 3 meters, right? And this is going to be 3 meters. And you know that is a right triangle, and isosceles right triangle, so it's going to be 45, yeah. Good questions. Right. So now we can solve for our equilibrium like we've done before. We get the force AF is going to be 5.66 kilonewtons in tension. I'm just rounding here, but this is the same thing. Alright, any questions so far? Okay. Now we're going to look at the next joint. I'm going to do joint F, actually. Okay. So by looking at our structure as a whole, we see that at joint F we have these different forces, and just keep in mind again the direction at which joint you're analyzing. If they share another force on like a different free body diagram, it needs to be equal and opposite, because when you think about it, we're taking each member apart, right? But when you put them back together, the different forces needs to cancel out for the whole structure to be in equilibrium. So for example here, right, we have AF force on both of these free body diagram, so we need to make sure that our arrows are equal and opposite. So when we put them back together, they're going to cancel and we still have equilibrium. But otherwise, as long as you stay consistent with your free body diagram, the numbers should be the same. And from looking at this structure, we see that this is going to be 45 degrees. So now we have all of our forces, and we can do equilibrium equation. Which is kind of the easy part. Alright. Is this the answer that everybody got? Okay. Now we're gonna move on to our next joint. I'm gonna do, let's do E. We know this is 45 degrees, 45 degrees. And if we analyze at joint E, then this is going to be 0. Because we see the y components cancel out. Now we can solve. So this zero force member is not as obvious, but force EB after solving your equilibrium equation is going to give you a zero force. So now that we've done let's see, we've done A, we've done F, we've done E. Now we can look at joint D. So at joint D we have P here, we have a force here, and like that. Oops. Okay, kind of ran out of space. The arrow's a little small, but that one is ED pointing away at 45 degrees. So if we do our sum of forces in Y, we can get the force ED. And if we do X, we can get CD. Any questions here? Okay. Now to finish the problem, we're going to look at joint C, which is the last one. And if we look at this, we see that the two X component forces kind of cancel each other out because they're the only X component present. So now to solve for the normal force here, Sorry, we're missing something. Then this will be the same as B. Oh, sorry, CE. Wait, oh. The force C. Wait, is my time up? Okay. Anyway, my time is up. Which one? Oh.
Okay, so this problem, there is not a by. What it is a FBC. So there is a vertical component, it's just FBC. It's not the reaction with B, it's the member force between B and C. So that's what the Y is.
That makes so much more sense. Okay. Sorry, guys. No 2 force member.
Okay.
So for problem 4, we're asked to determine the force in each member and state if they are in tension or compression. Right off the bat, we can identify a zero force member, and that is because CD and DE are collinear and BD is non-collinear. So analyzing at point D, it's pretty easy to see that BD is a zero force member. After this, I'm going to want to find what these two angles are. The way I'm going to do that is take the inverse tan of 5/12. It's going to give me this angle, and this angle is going to end up being equal to about 22.62 degrees. Then I'm going to want to analyze at point C first. So at C, we have this applied 300-pound force, and we also have CB and CD. So solving for my sum of the forces in the x direction, I have 300 plus plus CD sine of 22.62. And the reason I'm using sine of 22.62 is because you can see if we make a triangle here to find the x component of CD, you'll see that it's actually opposite to the angle that we solved for. And this is equal to 0. So CD is equal to 780 pounds, or negative 780 pounds, I mean. So that means that we know that this is in compression. We can then solve the sum of the forces in the y direction, and that's going to be negative CB minus CD cosine of 22.62. And that's going to give us that CB is equal to 720 pounds, which is in tension. All right, so we now know these two members, but we want to find now DE, BE, and AB. So I can't see another point that I really want to analyze at that has two unknowns. So I'm going to analyze at point D just to find what DE is. So at D, we have this free body diagram, DE, and DC. But we know that since BD is a zero force member, I don't even have to draw it on my free body diagram. And the equation that I'm going to get here is that since these are collinear, I know that F FDC minus FDE has to equal to 0. Or in other words, FDC is equal to FDE. This means that FDE, oh, I kind of switched my convention on how I was writing it. This means that DE is equal to 780 pounds. That's going to be in compression. All right, so now that we've found DE, we can move on to point B, because while this wouldn't have given me information about DE, I can find both AB and BE. My free body diagram here is going to look like this with BC, with AB, and BE. I'm going to go right into the sum of the forces in the x direction equal to, oops, I forgot, this 300-pound applied force at B. So that's going to be equal to 300 minus FBA cosine of 45 degrees now, because we're working with this angle rather than the red angles over here. So this is going to be also plus FBE. I keep changing my conventions. BA. Sine of 45.24. So, and what that 45.24 is if I have some angle here. And that's just based on, our 13 feet here and the other angles in the problem. Okay, so that doesn't really tell us much yet, but doing our sum of the forces in Y, we're going to get 720, which is BC upwards, minus BA sine of 45, minus minus BE cosine of that same 45.24. So BE is going to end up being 297 in tension, and BA is going to end up being 722 in tension as well. So there are a lot of different ways to do this problem. This is just what I found the easiest, but you could also analyze the entire free body diagram, or try to. You're going to notice that it's going to be pretty difficult to solve for both AY, AX, EY, and EX. But you do not have to break it up in the way that I did. I just think that this is the easiest because throughout the whole thing I didn't have to analyze at any joints that had these reaction forces. I could go, from top to bottom where I had, this known and two unknowns, and just keep working my way down. So that's what I would do for problem 4. Moving on to problem number 5. We are given a 2-member truss, and we're asked to find the angle so that the force in either member does not exceed 400 pounds in tension or 200 pounds in compression. So what that means is that we're going to have a range of what the angle could possibly be. But the way I'm going to have us solve this is just starting out like a regular truss problem. So I'm going to start by analyzing at point A. And drawing the free body diagram at point A, you'll see that we have this AB, this AB, and some 300 pounds here. The sum of the forces in the x direction is going to give us 300 cosine of some angle plus AC plus AB times 4 over 5, because you'll see that this entire triangle is a 3, 4, 5 triangle, where 5 is on the hypotenuse. It's going to all be equal to 0, right? So for our sum of the forces in the y direction, we're going to have minus 300 sine angle plus AB times 3 over 5 equal to 0. This will allow us to solve for AB in terms of, the sine of this angle. So we're going to get that AB is equal to 500 sine of this angle, and we know that this has to be less than or equal to 400, which is in tension, or greater than or equal to negative 200, which means that it's in compression. So then we can plug this back in to our sum of the forces in the x direction and get an equation for AC as well. And what that's going to look like is AC is equal to negative 300 cosine of some angle minus 400 sine of some angle. And then once again, we're going to impose the same constraints onto it. Simplifying these down a little bit, what we're actually going to end up with is just negative 2 less than or equal to 5 sine angle less than or equal to 4, and negative 4 less than or equal to 3 cosine of some angle plus 4 sine of some angle less than equal to 2. And the reason you'll see that we've, switched where the 400 and negative 200 originally were is because we divided by negative 1 to get rid of these minus signs, which means that we have to switch our constraints as well. So, combining these two together to get some new function, we'll get that we have some negative 0.4 less than or equal to this function g1, which is equal to the sine of this angle less than or equal to 0.8. So you can see that comes from this equation. And then from the next equation, we're going to get negative 1 less than or equal to some function g2, which is equal to 3 over 4 cosine of angle plus sine of some angle, which is less than or equal to 0.5. So, this is eventually going to give us the final answer, which is that we have, we're going to be between the degrees of negative 24 and negative 13 degrees. So use your calculator for that. You can also do it in radians, but for this, it also says, hint, solve for trigonomic equations graphically. And we're given, or we can graph the first equation such that it looks like this. We've got 0, 0 here. And it just looks slightly like that, going up to about 0.8 and 0.6. You would do this, not by hand, with a calculator or, online graphing calculator. For this one, we're going to start down here. We have first kind of this way with negative 1.5 over here, and negative 1.8 over here. And this would be negative 1.0 as well. And you can see, like, counting the angles in a counterclockwise direction, these two constraints are only satisfied by these numbers. So kind of the gist of it is we want to be able to satisfy both of these equations, which you can demonstrate visually with these two graphs. To clarify a little bit about the use of these graphs, this first graph is G1 versus the angle theta, and this is G2 versus the angle theta. So what I'm doing is literally just graphing these two equations that I have, or these two inequalities that I have. And G1 is between negative 0.4 and 0.8. So if, like, down here is negative 0.4 and negative 0.8 is, like, somewhere up here. And G2 is between negative 1 and 0.5. What I'm getting at here is that since we need a theta that's going to satisfy both of these equations, so we can really only go from negative 0.4 to 0.5, because if we go to 0.8, we're not including some of G2, and if we go to negative 1, we're not including some of G1. So what that's going to look like is just between those specified values on the graphs, you know, the angles that we have there. So here it's going to be from negative 0.4 to, like, let's say 0.5 is here, negative 0.4 to 0.5, and down here just from negative 0.4 to 0.5 as well. So if we'll say negative 0.4 is, like, here, we'll be going just there. Those angles, we have some overlap for just those angles, you can see. But the way to solve it numerically is to do the sine of this angle and sine of this angle, or 3 over 4 cosine of the angle plus the sine of the angle, to setting those equal to these values to calculate for the extreme constraints. For this next truss, we're asked to find the forces in members HD, CD, and GD and state if they're in tension or compression. So with this one, I'm going to use both the method of sections and the method of joints. But first, let's analyze the entire structure. So first, I'm going to draw my free body diagram just as a little rectangle. I'm going to have AY, AX, and EY. Off the bat, I'm going to solve my moment at A because I'm planning on doing the method of sections only on this side of the truss. So I don't really need to know what the reaction forces at A are. So I'm just going to solve the sum of my moments at point A to get what EY is. And what I'm going to get from this is EY times 16 meters minus 40 times 12 meters minus 20 times 8 meters minus 20 times 4 meters equal to 0. And this is going to give me EY is equal to 45 kilonewtons. Now, going into the method of sections, let me draw out another free body diagram here. I'm going to have one full square, and then I'm going to cut the members HG, HD, and CD. So this is HG, this is HD, and this is CD. Don't forget that we have Y here and 40 kilonewtons here. The first thing I'm going to do is solve for the moment about H. So H, you can see, is here. It's not even in this structure. But solving for the moment about H is going to allow us to solve for CD, which is one of the members that we actually want to solve for. An alternative method of doing this would be to solve for the moment at D and find what HG is. However, HG we actually aren't asked to solve for, so it would just be a little bit of additional work. So solving for the moment about H, we'll get our 45, which is EY, times 8 meters minus 40 times 4 meters, which is that 40 kilonewtons, minus FCD times 4, which is equal to 0, which will allow us to find CD off the bat, and that's going to be 50 kilonewtons in tension. Then it's easy to go to our sum of the forces in the y direction, since neither HG or CD contribute to the sum of the forces in the y direction. And we're going to get 45 minus 40 minus minus HD sine of 45. This allows us to solve for HD to be 7.07 kilonewtons, and that's in compression. It's negative 7.07 kilonewtons, meaning that it's in compression. Now, the last thing we're asked to solve for is actually GD. So that isn't a member that we cut along, so we're going to have to use a different method. You could use another cut, but I wouldn't recommend it. I would instead recommend joint analysis at point D. So at point D, I'll draw a new free body diagram. We have something that looks like this, where we have that G that we're looking for, DE, HD, and CD. Luckily, we have already solved for CD and HD, so we only have two unknowns. And since we're only looking for GD, we can just use the sum of the forces in the y direction, since sum of the forces in x direction isn't really going to tell us anything useful to what we need for this problem. So this is going to be equal to GD minus 7.07 sine of 45. And that's going to give us that GD is a positive 5 kilonewtons, meaning it's in tension. So that is going to be how to solve for each of those three values. Okay, so doing problem 7, we're asked to determine the force in each member and state if they're in tension or compression. Automatically, when it tells me that we want to determine the force in each member, I think of doing joint analysis. I just find it easier that way instead of making cuts everywhere, since we have to find, each and every single force in each member. So I'll start out with our entire free body diagram analysis. So there we're going to have a X, a Y. We're told that this is 40 kilonewtons, and we're told that this is 20 kilonewtons. This is EY, and from here we can do our sum of the forces in the x direction equal to 0, and that is just AX, so we know that that force is 0. Sum of the forces in the y direction is AY minus 60 plus EY equal to 0. Can't get anything from that yet, so we'll do the sum of the moment. You can do either A or E. I did A, and this is equal to negative 1.5 meters times 40 minus 4.5 meters times 20 plus EY times 6, this all equal to 0, and it's going to give us that EY is equal to 25 kilonewtons. And that AY is equal to 35 kilonewtons. So now we're going to start doing our analysis at the pins. For me, I like to start somewhere where I have the most amount of knowns and least amount of unknowns. So that's going to be at A, where I know AX and AY, and I just have to find AB and AG. Something else that we're going to need to know is what this angle is. And this angle is equal to the inverse tan of 2 over 1.5. And that is 53.1, just about. So drawing my free body diagram at A, I have AB and AG. And then I have my reaction forces AY and AX, which I know is 0. So doing the sum of the forces in the y direction first, I get that AY plus AB sine of 53.1 is equal to 0. And I know that AY is 35. So what this is going to give me is that AB is equal to about 43.8, about negative 43.8, which means that it is in compression. This is this angle here, so you guys know. And then after doing this, I'm going to jump immediately into the sum of the forces in the x direction, which is AG plus AB cosine of 53.1 equal to 0. AG minus AG is equal to 26.3 in tension. Now that I know that, I'm going to analyze at B. And my free body diagram is going to look like this, where I have BC, AB, and BG. My sum of forces in X is going to give me negative AB cosine of that same 53.1 plus BC equal to 0. And BC there is going to be equal to negative 26.25 in compression. And same for the sum of forces in the y direction. Since we have solved for what AB is, we can solve both of these really easily. Minus BG equal to 0, which will allow us to solve for BG, which is going to be 35 in tension. Alrighty, back to our free body diagram. What I do next is go to point G, because at G we now just have these two unknowns that we have to solve for. And what that free body diagram is going to look like is BG, CG, GF, and AG. And don't forget that 40 kilonewtons downward. This looks kind of complicated, but remember that we still just have two unknowns, those being CG and GF. So our sum of the forces in the y direction is going to give us BG plus CG sine of 53.1 minus 40 equal to 0. And that's going to give us CG equal to 6.25 in tension. Sum of the forces in the x direction is going to give us negative AG plus GF plus CG cosine of 53.1 equal to 0. And that's going to show us that GF is equal to 22.5 in tension. Let me now just reduce down the size of this so that we have more room to work. And now that we've found GC and GF, I'm going to go to joint C, because we can then solve for CD and CF. what that free body diagram is going to look like is we have BC, CD, CG, and CF. The sum of the forces in the y direction is going to give me negative CG sine of 53.1 minus CF sine of 53.1 equal to 0, and that's going to result in CF equal to 6.25 in compression this time. Oh, it's negative 6.25 in compression. The sum of the forces in the x direction is going to be negative BC plus CD minus CG cosine of 53.1 plus CF cosine of 53.1 equal to 0. This is going to give us that CD is equal to negative 18.8, so that's also in compression. With that, we're going to move on to joint D. So at joint D, we now just have to find DF and DE. That free body diagram is going to have CD, DE, and DF. The sum of the forces in the x direction there is going to give us the equations negative CD plus DE cosine of 53.1 equal to 0, and that's going to give us DE equal to negative 31.2 in compression. The sum of the forces in the y direction is going to give us negative DE sine of 53.1 minus DF equal to 0. And since we just solved for DE, we'll be able to solve that DF is equal to 25.0 in tension. Now there's just one more member to solve for, which is EF. So I did the free body diagram at E. So down here I'm going to do the free body diagram at E, which is DE here, EF here, and EY here, which is my reaction force in the y direction at E. For this, we're only going to need the sum of the forces in the x direction, since we're just trying to find EF, which is equal to negative EF minus DE cosine of 53.1, which is equal to 0. And solving that is going to give us that EF is equal to 18.8 in tension. So after going through all of that, we have found the force in each and every single member. For problem 8, we're first asked to determine if there are any zero force members in the truss. So this one's actually pretty difficult, but you'll see that if you analyze the structure at point A, I'm going to draw the free body diagram there, that you have AN, AB, and since A is a roller, you only have AY, no AX component. And what this is going to tell us is that AB has to be a zero force member because there are no other horizontal components. You see AB has a horizontal component, but there is nothing to counteract that. So that member has to be a zero force member. Now for B, it says to determine the axial forces in members LK, LD, and CD and state whether these members are in tension or compression. So the problem already shows how I would cut it and analyze either the left or right side of the structure. I'm going to analyze the left side of the structure, but to start, depending on which way you're doing it, you can do this same start to how to approach this problem, which is to analyze the entire free body diagram. So going to sketch it out. This is kind of what our truss looks like, and we have 1,000 pound force here, 1,500 pound force here, and 1,000 pound force here, and a 900 pound force here. We also have that AY component, as well as our reaction forces at C, or our reaction forces at G, excuse me, GY and GX. So the sum of the forces in the X direction is going to give us 900 plus GX, which is equal to 0, giving us that GX is equal to negative 900 pounds. Sum of the forces in the Y direction is AY plus GY minus this 3,500 from all of those downwards forces. And this is equal to 0. We can't really do anything with that yet, so I'm going to find our moment about G in order to find what AY is. The sum of the moment about G is going to be 1,000 times 16 plus 1,500 times 24. And I'll move this over. Plus 1,000 times 32 minus 900 times 24 minus AY times 48 equal to 0. And you should be able to get all this from the distances that you're given on the free body diagram, as well as how they will make the structure rotate about point G. So solving this whole thing, we're going to get like we're going to get that AY is equal to 1,300 pounds. And plugging that back into our sum of the forces in the Y direction, we're going to get that GY is equal to 2,350 pounds. Or, excuse me, that's incorrect. We're going to get that GY is equal to 2,200 pounds. But you don't really need GX and GY if you're solving the left side of the free body diagram. So if I'm solving this left side of the structure, I only really need AY. And I'll draw that out now. What that's going to look like is I'll have this side of the truss where I have my LK, LD, and CD coming out, because those are the three members that I'm going to be solving for. And here I have my AY, and here I have that 900 pound and 1,000 pound. So you can see that I have literally just mirrored this side of the original drawing. And the very first thing that I want to do here is take the moment about L. And the reason that is because taking the moment about L, I'll only be including one unknown in my moment equation, which is CD, because I know what AY is, and I know these, all of these forces at L are not going to contribute to the moment equation at L. So it's actually very simple. It's just the sum of the moment at L is equal to CD times 8 feet minus AY times 16 feet. And since we know what AY is, we can really easily solve that CD is equal to 2,600. And this is in tension. This then makes it easy to solve our sum of forces in the Y and X direction. So starting with Y, we have AY minus 1,000 minus LD sine of 45 equal to 0. It's 45 because you can see that all of these triangles have 8 both as their X and Y dimensions. And this is going to give us that LD is equal to 424 pounds in tension. The last equation we're going to have to solve is the sum of the forces in the x direction. And this is going to be equal to 900 plus LK plus CD plus LD cosine of 45, which is equal to 0. But since we already know what both CD and LD are, we can solve for LK. And that's going to be negative 3,800 pounds in compression. So these are the three forces that you were asked for, and that's how you solve the problem. For problem 9a, we are asked to circle all of the zero force members in the truss, and assuming that all connections are pin connections and self-weight is negligible. So we learned about two different ways to identify zero force members. The first of which that you have two collinear and one non-collinear member. So let me write that out. The first rule is if you have two collinear plus one non-collinear member at a joint with no applied forces, then the non-collinear member will be a zero force member. So off the bat, we can identify a lot of these in this truss. The first one that I noticed is going from left to right. We have these two collinear members and this one non-collinear member. So we know that that non-collinear member is got to be a zero force member. And the same is true opposite of it right here. And the same is true on the other side of the truss here and here. You'll probably also quickly notice that at the top you have two more collinear and one non-collinear members at this joint right here. So that means that this has to be a zero force member. Now, the last one of this kind to identify is a little bit more tricky, and that is if you analyze at this point. So at this point, you'll see that you have two collinear members here, but it looks like there are three non-collinear members coming off of this joint. And when you have, more than one non-collinear member coming off of a joint, then usually you cannot use this rule to analyze if they are zero force members. But since we know that these two members are already zero, it's essentially as if we have something like this, where these two members aren't even here, which would show us very quickly that this is a zero force member as well. That one's a little bit tricky, but that's the rule there. I'll bring back our zero force members here. And then the second rule that we have is if we have two non-collinear members with no applied forces, then both are zero force members. So if you look on our truss, you'll see that at this joint you have two non-collinear members, no applied forces, so both of these are going to be zero force members. One other pitfall I did want to point out for you guys to avoid is that even though for this member over here we determined that this would be a zero force member, the same is not true on the other side, because you do have an applied force at this at this joint that you're analyzing at. So this would not be a zero force member. So just to clean it all up a little bit, you're going to end up with zero force member here, 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 and here. All right, moving on to 9B. It's asking us to compute the force in members ED, EM, LM, and OP. So you can see where those are on this diagram. I'm highlighting them now. And for this question, I'm going to use a bit of a combination of a couple different methods. So I am both going to cut here and do joint analysis here. So I put this problem on another page just so that we'd have a little bit more room to work. But starting out, I'm just going to analyze the entire structure first. And what we have is this kind of trapezoidal truss where we have a 75-pound force downwards, a 100-pound force, and we have reaction force AY, PY, and PX. So solving this, we get the sum of the forces in the x direction equal to 0, which is PX minus 100, giving us that PX is 100 pounds. Sum of forces in the y, I'm not going to do yet just because I know I'm not going to be able to solve it without our moment equation. And I'm going to do the moment about P so that I can solve for AY. Setting this equal to 0, we have 100 times 14 feet plus 75 times 5 feet minus AX times 12 feet. And these are all given on the free body diagram. This will give us that AY is equal to 148 pounds. Then solving for the forces in the y direction, we have that AY plus PY minus 75 is equal to 0, and PY is going to be negative 72.9 pounds. Okay, awesome. With that, I'm going to solve the upper part of our truss. So I'm going to solve up here. I'm going to solve up here just because I think it'll be a little bit easier to use the 75 and 100 instead of using, AY, PY, and PX. And I'll draw out what that looks like down here. We're going to have the same trapezoidal structure, but with LM, ED, and EM exposed. Oops. We have, this is what it looks like. And we have that 75 pounds and 100 pounds still. The first thing I'm going to do is solve for the moment about E, because I know I'll be able to get LM from that. So the sum of the moment around E is negative 75 times that horizontal distance from E to where 75 is located. and we're going to have to do a little bit of trigonometry to figure out where that is. So I'm going to go back up to our truss here, and we're trying to find this distance x. So what we do know is that this is the same as doing this distance x here. And I think that'll just make it a little bit easier to see how this is a similar triangle with this triangle that I'm laying out right now. So solving for the angle here is going to give us that same angle up here. And this is the reverse tan of 14/7, which I just get from this 14 and then 12 minus 5. And that's going to be 63.4 about. So we know that this angle up here is the same. We also know that, I believe it tells us that the horizontal members are evenly spaced, and that's important because we know then that since there is 7 gaps between each horizontal member, that each of them is just 2 feet tall. So we know that this entire segment here is going to be 6 feet tall. So now we have this triangle where we know the angle and we know one of the side measurements. So to find x, I do the inverse or the tan of 63.4, and that's equal to 6 over x. X is going to be 6 over the tan of 63.4, and x is going to end up just being 3. So down here, we can come back and say that it is negative 75 times 3, and then plus 100 times the distance. You're just going to want the vertical distance, so it's just times 6. And then continuing on, we do minus LM, which is down here, times 8, which is that 3 we got before, plus we know that this dimension is 5. So 5, and we know that dimension now is 3. And all of this is going to be equal to 0, so we're going to be able to solve for LM, which is going to be 46.9 pounds in tension. Solving onward, we have the sum of the forces in the x is equal to negative 100 minus ED cosine of that same 63.4 degrees that we found before, plus EM cosine of this angle here. So here, I'll call this angle like that, just to differentiate them. So to find this angle, we're going to need to do a little bit more trigonometry. So I'll bring us back up here and just kind of erase what we've done here to make it a little bit easier to see. Because the angle that we're looking for is between EL and EM. What is this angle? We know that our dimension over here is 2, and we know that our dimension over here are 3 and 5, making this entire thing 8. So you can really easily solve that the inverse tan of 2 over 8, which is going to give us about 14.0 degrees. Alrighty. So now that we have that, and this is equal to 63.4. Now that we have that, it's going to be, we're going to want to put that here, 14.0. And this is all equal to 0. We can't really do that much with this yet. So I'm going to write out our y equation, which is going to be negative 75 minus LM minus ED sine of 63.4 minus EM sine of 14.0. So you'll notice that both of our equations have two unknown variables in them. So I am going to do substitution in order to solve for them. Starting with finding EM in terms of ED using some of the forces in the X equation. Do it in a different color so it's a little easier to see. But what I get from here is that 100 is equal to 0.97 EM minus 0.45 ED. And that's just me solving our cosines here. And then from that, we get that EM is equal to 100 plus 0.45 ED over 0.97. And this is equal to about 103 plus 0.460 ED. So plugging this value of EM in terms of ED back into our y equation now, we're going to get negative 75 equal to 46.9 plus ED times what this is, which is 0.894 plus 103 times 0.243, which is what the sine of 14 is, plus 0.460 times 0.243 ED. And that is just me multiplying these numbers by the sine of 14. So what this big equation is going to give us eventually is that negative 146.9 is equal to 1.01 ED. And then from that, we get that ED is equal to about negative 146 in compression. So that part's a little bit confusing, but basically we're just using substitution in order to find ED and EM. So now taking ED here, we can bring it back up to our equation for EM, plug it in over here and solve that EM is equal to 35.8 in tension. Alrighty. So from that, we've now gotten, let me try to make this a little smaller. From that, we've now gotten 3 out of 4 of the member forces that we were looking for, which is really nice because solving for OP is going to be a lot easier. So I'm first going to put what we've solved for already into our table here. It's going to be negative 146 pounds. Make sure to put your units there because that is something that they are looking for when grading. Make sure you have pounds in your magnitude. So we solve for all of these. We know that this is in compression, tension, and tension. And now we're just solving for OP. And the way we're going to do that is just by solving at point P. And I'm just going to draw a little free body diagram where we have PO upwards and we have 100 pounds, which is what our reaction force in the x direction at P is, and 72.9 pounds downward, which is our reaction force in the y direction at P. And then we also have this AP. But it is very clear from this free body diagram that PO is just going to be equal to 72.9 to counteract in the y direction. We can write it out if we want. Some of the forces in y are equal to PO minus 72.9 equals 0. And that's going to give us that PO is equal to 72.9 pounds in tension. So 72.9 pounds in tension. Alrighty, that's how you solve number 9B. We are now moving on to solving frame problems. So looking at this first one, it shows us a frame with a 400 pound applied force, and it tells us that D's a pin, E's a roller, and it's asking for us to determine the support forces that act on member ACE. So that's something important to remember when you're solving this problem, is that at the end you want to report your reaction forces at A, C, and E in terms of what they are directionally on ACE, because if you report, C in terms of its directionality on BCD, then it's going to be different from what they're actually looking for. So starting out, I would usually with frame problems assess the entire frame first. So what we have here is that 400 pounds downwards with dx, dy, and EY reaction forces. So the sum of the forces in the x direction is going to tell us that dx is equal to 0. Some of the forces in the y direction is going to tell us that dy plus EY is minus 400 is equal to 0, which we cannot solve without doing the moment at either D or E. I did the moment at D. And what that's going to give me is negative 400 times 6 plus EY times 8, which is equal to 0. This is going to give us that EY is equal to 300 pounds, and that when we plug this back into our sum of the forces in the y direction, we're going to get dy equal to 100 pounds. So moving on, the next member that would immediately jump out to me as what I'd want to analyze is AB. So this top member here. And I would want to analyze it because I know that if I use my moment equations well, that I'll be able to solve for both AY and BY. And I'll show you how to do that. So we have that 400 pounds down, we have AX and AY, and we have BY and BX. Right off the bat, I know that I'm not going to be able to solve for AX or BX here. We're just going to get like the sum of the forces in the x directions equal to AX minus BX equal to 0. And I can't really do much with that. But I know that if I solve for the sum of my moment at A, that I'll be able to solve for BY, because since BX is collinear with A, it's not going to contribute to a moment, so the only unknown that's going to be contributing to a moment about A is BY. And the way I'll set up this equation is having negative 400 times 6 plus BY times 8. Solving that, we're going to be able to get that BY is equal to 300 pounds, and consequently AY is going to equal 100 pounds. With that, having AY, I now want to move on to actually analyzing ACE, which, if you remember, is what we want to determine the support forces on. So, ACE, I'll go like this. Remember to switch the direction of your reaction forces now, especially like for AY here, you can see that's very important. And then CY and CX I'm just going to do arbitrarily, and EY I know from my entire free body diagram is upward. So the sum of the forces in the x direction here is going to give us CX minus AX equal to 0. Can't do anything with that yet. But the sum of the forces in the y direction is going to be CY minus AY plus EY. And we know what both AY and EY is, so we can solve for CY here. So CY minus 100 plus 300 is equal to 0, giving us CY is equal to negative 200 pounds. Equal to 0. And the reason that I find the sum of the moment about C in particular is because I know EY and AY, so the only unknown that I'll have when I solve the sum of the moment about C is AX. If I did the sum of the moment about A or E, I'd have multiple unknowns to solve for. So using this equation, I'm able to say we have 100 times 4 plus AX times 4 plus 300 times 4 equal to 0. And that's going to give us that 4AX is equal to negative 1600, and that AX is thus equal to negative 400 pounds. Bringing that back up to our sum of the forces in the x direction, we get that CX is also equal to negative 400 pounds. And you can leave your answer like this because according to your free body diagram, the grader should be able to tell the actual directionality of your forces on this member, but I will just write it out in Cartesian form because I think it kind of highlights which direction the forces are actually acting on ACE. Because we know that CE is negative, AX is negative, or excuse me, CX is negative, AX is negative, and CY is negative, which means that they are actually all going in the opposite direction of how we've drawn them. And what that's going to look like is my force C is equal to negative 400 I hat minus 200 J hat pounds. My force A is equal to 400 I hat minus, minus 100 J hat pounds. You can also do the force E, which is just going to be 0 I hat plus 300 J hat pounds. And that's how you solve that frame problem. We'll move on to the next frame problem where we have a frame that includes a pulley. So these can be a little bit confusing, but they're actually really not harder than any other frame problem. So some important things that are in this problem is that it says the pin at B can only support loads up to 24 kilonewtons. So it's asking you the maximum mass that can be supported. So in this problem, instead of solving for, the reaction forces or the forces in a member, you're solving for a mass based on what you know about pin B. So this can be a little bit confusing because it kind of feels like you're working backwards a bit. But I would say when you first read that, the first thing you should do is think about, you know, which pins do I actually need to know the forces for? Because you could go through this whole problem, you know, maybe you didn't read that, maybe you didn't read any of this stuff here at the top, and you just go and you solve for every single reaction force at every single member, and you actually did a bunch of work for some information that you didn't really need. So what I would do first is consider, oh, this means that my magnitude of B can be at most 24 kilonewtons, which means that I'm looking to find the By and Bx components of reaction forces at B, because, you know, the magnitude of B can be solved by doing the square root of Bx squared plus By squared. So those are what I'm looking for here. With all that said, the first thing I'm going to do is analyze our pulley. So if we isolate the pulley itself, we'll see that we have some weight going this way, some weight going this way, and I'm just going to leave those as a variable. And then at point D here, we have some reaction force dx and some reaction force dy. And analyzing this, it's pretty easy to see that our weight is equal to dx is equal to dy. So that'll be important to keep in mind as we're analyzing the rest of the truss. Now that we have some information about D, I'm going to want to choose a member that is connected to D. So next I'm going to look at BDE. Drawing this free body diagram here, we have, this is BDE. I'm going to switch the directions of my dy and dx. And I'm going to put in EY, EX, BY, and BX. I know right away that I'm only really concerned with finding what my reaction forces at B are. So I'm going to skip straight to finding the moment at E, because I know that that'll give me some information about what BY is. So the moment at E is going to give us the equation dy times 400 minus by times 700. And that's equal to 0. And since we know that dy is just the weight, we get that by is equal to 4/7 times this variable that we've made up, the weight. That's all that I really want from that member. So now I'm going to go and analyze A, B, C here to hopefully get some more information about what Bx is. So here we're going to have Bx and By, switching the directions that I'm drawing them once again. We're going to have our weight here. We're going to have Cy and Cx. And we're only going to have a y component of A. Now, this might seem a little confusing because you can see very clearly on our structure that A is a pin, so it should have an x and y component. But when you're solving the entire free body diagram of the whole truss, you'll see that our only reaction forces are AY and AX and FY. So very clearly the sum of the forces in the x direction are equal to 0, and they're just equal to AX because it's our only reaction force that has a component in the x direction. So I'm not even going to draw AX on here, and I'm going to jump immediately to solving the moment at C. And the reason I want to do this is because, once again, I'm only interested in finding information out about B. So some of the moment about C. So for the moment about C, what we're going to get is the weight times 500 millimeters, which you can see up here. And then we're going to do minus bx times 600 millimeters. And that's the entire moment equation about C. And what this is gonna give us is that bx is equal to 5/6 times w. So now we have both bx and by in terms of w. And remember, I had this initial equation up here. I'm gonna bring that down here. And I'm gonna use what we now have solved for in order to solve for what w is. So we have 24 is equal to the square root of bx squared, which is 5/6w squared, plus by squared, which is 4/7w squared. Solving this, you're gonna get that 24 is equal to about 1.01 w, and w is equal to 23.75 kilonewtons. So we're almost done, but the question did ask for the maximum mass, not the maximum weight. So we're going to go ahead and divide this by 9.8, or your gravitational acceleration. And what we're going to get from that is that the mass is equal to about 2.42 kilograms. Or I think rather equal to 2,420 kilograms. All right, and that is how you solve problem 2. And that's all. Alrighty, so we're now going to start with solving some machines. And machines tend to look a lot more complicated than they actually are. So it's important to just remember to, cut at your pins, detach different parts from one another, and make it a whole lot easier to solve each component. I think it's really easy in machines to accidentally spend a lot of time solving for things that you don't really need. But we're going to try to build your intuition to avoid that. So starting with question 3 here, the first thing that we want to identify is if we have any two force members, because those can really simplify solving these problems. So first one that I see is AB, since we have 2 pin joints here, so AB is going to be a 0 force member, and also DF is going to be, excuse me, I said 0 force member, I meant 2 force member. Both of those are going to be 2 force members. Since AB is a vertical 2 force member, we're just going to have AX and BX. Or AY and BY, sorry, I misspoke. I'll just draw it. AY, BY. So then if we look at member BC, this big member here, applying this knowledge, we should be able to see that there is also no horizontal component of C, and that's because if I have, CX and CY here, there's going to be no other horizontal members on this entire piece of the machine, meaning that we're only going to have a CY component, and that CX component is going to become 0. So this would be some CY. So that'll make CDE a 3 force member, because you're just going to have this force DF and some force E here and CY. So this can be a little confusing, because you're like, at E, I'm seeing that we have a pin, so there should be, an X and Y component. So let me draw that out to just explain it a little bit further. we've got C, D, and E here. So starting out, we have CY in some tension DF, and this EX. And the reason that that doesn't have a vertical component is because as a 3/4 member, remember that one way to identify a 3/4 member is that each and every single force acting on it conjoins at a single point in space. So let me draw that out. CY going this way, DEF going this way. In order for E to also correspond to this joint point, EX has to have, or E has to have no vertical component, because if it does have a vertical component, then the line is going to look something like this or this, and it'll never conjoin at that same point that CY and TDF is joined at. So our knowledge that this is a 3/4 member, because we have 3 forces acting on it, tells us the directionality of EX. And that directionality, or it tells us the directionality of E, and that directionality is that it's only on the X plane. Hopefully that makes a little bit more sense. That's a bit of a tricky topic. But this is going to be really helpful in solving our whole machine. So now I'm going to draw another free body diagram. And I'm going to do it of BC, including that big fork structure. So we have this line, essentially, and some L shape where there's a weight applied. And then we also have some BY, as we identified earlier, and some CY, as we also identified earlier. And this is going to give us a couple equations. I'm going to jump right to our moment equation about B, because that's going to tell us a little bit more about CY, because we know what the weight is. The weight is 8 kilonewtons. So the sum of the moment about B is going to be equal to 0.2 CY minus 0.9 times 8. It's going to be equal to 0. So CY is going to be equal to 36 kilonewtons. So remember now that we're finding the forces that the pins on member CDE experience, so you don't really need to know what BY is at all. Alrighty, so now we can go back to this free body diagram that I've drawn up here. And, you know, notice that I have drawn CY in opposite directions on these two free body diagrams, which is really important. And this means that even though we solve CY to be a positive upwards force on the member BC, it's going to be a downwards force on CED. So that's just something good to keep in mind, because you're asked to find the forces that the pins on member CDE experience. So it's going to be in reference to that member instead of this member. All right, so I'm just going to jump into solving some equations here, starting with the sum of the forces in the x direction. We're going to get that negative EX plus T dF cosine of some angle. And this angle is this angle here. And that's equal to 0. We're also going to get that the sum of the force in the y direction is equal to negative CY minus T dF sine of that same angle equal to 0. So we can determine what this angle is just based on the geometry here. And after finding what that is, it's going to be tan, inverse tan of 0.3 over 0.2. Plug that in over here. We're going to get from this that CY is equal to negative 36 J hat. And then EX is equal to 24 I hat. EY is equal to 0. DX is equal to negative 24 I hat. And DY is equal to 36 J hat. All of these are in kilonewtons. And remember from earlier that we said that CX is equal to 0 as well. So these are all in Cartesian coordinates with reference to the member CED. And what that means is that CY is negative 36 J hat in terms of this structure, because we solved it to be positive down here. So bringing it back up over here, we'll also have that it's positive here, so a positive 36, but positive in the opposite direction. So putting that into Cartesian coordinates, negative 36 J hat. That can be a little bit confusing. And just doing the same for everything else, here we'd solve that EX is actually negative 24. But since it's negative 24, that means that we drew the direction of this arrow incorrectly, and that it's actually going in this direction, which means that it is in the positive I hat direction. Then we just do the same for everything else to solve for our 6 different components. Hopefully that makes a little bit of sense. So for question 4, we're asked to analyze this rotating arm hinged at A and B that actuates a piston at C. And the pressure from this chamber that the piston extends into results in a 5 kilonewton force pointed to the left on the piston. And we're asked to determine the couple moment N as our final goal required to prevent motion of the piston. So a couple things to keep in mind. First, in static mechanics, nothing ever moves. So this piston has the ability to move, but in this problem, that couple moment M is going to prevent it from moving, and that's what we want to find. The other first thing we want to consider is looking for 2 force members. Right off the bat, I've already drawn out that at B and C, you have matching reaction forces. That's going to result in BC being a 2 force member. So it's going to have some, we'll call it TBC, that acts collinear to that member. So now I'm going to analyze at point C and point out a couple things. So at point C, we have this tension BC, as I mentioned, but we also have this 5 kilonewton force. And what we are kind of confused on here with this 5 kilonewton force is, if we only have a force in the x direction, then TBC is just going to end up being 0 because it has no, or it's not going to end up having a y component, which doesn't make sense because we know that it has to be collinear with BC. So that would mean that BC is just lying flat, which it is not. So we also have to consider the normal force from the walls of the cylinder. So this might sound a little bit more like physics 1 with, your normal force and the pressure here. But the normal force is going to contribute this force upwards that I'm going to call this CN to represent normal. And what I'm going to get from this free body diagram is try to find what TBC is. It's important to find what that angle is to find TBC. And this angle is going to be the inverse tan of 212 over 278. Just take my word on that for now, but you can solve that using the geometry of this triangle here. That is this angle as well as this angle. So hopefully do that on your own and hopefully get the same angle, which is 37.31 degrees. Alrighty, so as I said, I want to find what TBC is. So the easiest way to do this is just by taking my sum of the forces in the x direction. So that is -5 plus TBC. Oh, sorry, I wanted to have this going this way to oppose my 5 kilonewtons plus TBC cosine of whatever this angle is. That's equal to 0. From this, I can get that TBC is equal to 6.28 kilonewtons, and that's in tension because it's positive. So now that we know that, we're still looking for what this couple moment M is. So I want to analyze AB. The free body diagram of AB, here, let me do it in a different color. It's going to look like this, where we have that same tension TBC going in the opposite direction. Now, always remember to flip the direction of your forces, but we're also going to have some reaction forces AX, AY, and of course the reaction moment. So since we're only looking for the moment here, right off the bat, we want to solve our moment equation. And I'm going to solve the moment equation at A, since we know what TBC is, and I don't want to solve for what AX or AY is. So my sum of the moments at A is going to be equal to -M, just because it's drawn going in the clockwise direction, plus 212 millimeters times TBC, sine of this angle, plus 212 millimeters times TBC cosine of this angle. And what we're going to get from that, setting it all equal to 0, is that our moment is equal to 1.87 Newton meters, or negative 1.87 Newton meters K hat. So this is in Cartesian coordinates. This is just based on how we've drawn our free body diagram, and it is the equivalent to this in Cartesian coordinates, which is just pointing out that it is indeed in the clockwise direction, which you can see either visually from our free body diagram or based on the fact that it is in the negative K hat direction. All right, so I do just like to point out something about moments, because I see a lot of confusion about this, is that the sum of your moments at a point, so I'm going to use A as a reference. My sum of my moments at A still includes this reaction moment at A. So it still includes that negative moment, even though it is situated about A. I see a lot of people confusing the sum of the moments at A with the reaction force, like maybe this is called MA, the reaction force MA, but they are different because your sum of the moments at A is always going to be equal to 0, because it is the sum of every moment due to every force acting on that member. But your reaction moment at A is going to have a value, and what that reaction moment is it's counteracting all of the other moments that are generated by forces along the member. So it's going to be the opposite of what your combined moment from all the other forces on the member actually are. So plus some moments due to other forces. And that's all going to be equal to 0. So hopefully that clears up a little bit of confusion about how we solve for our reaction moments. Okay, so starting question number 5 here, we have a bucket and arm connected to this excavator that can support a 7.5 kilonewton load centered at G. So you can see that they've drawn that in there. And all of our connections are pins as per usual. A, B, D, E, and F, I are hydraulic cylinders, which you're going to see means that they are 2 force members. And it says to determine the force exerted in cylinders A, B, and F1 if the arm and all components are to remain static, which of course they always are in this class. So the first thing, of course, to notice is our 3 force members, cylinders F1, AB, and DE. All of these are 2 force members, and we now get started with separating out our different members. It's important to think about where you can cut to make different sections. So any of these pins that I'm highlighting at, you can cut at to form different, different members. But the easiest thing to do, I think, is to break it up into this bucket and this member A to J, and this kind of horizontal member from C to H. What that's going to give us is the ability to kind of find those internal forces at IF and AB. So firstly, I'm going to start with this IG bucket. Here we're going to have a free body diagram that kind of looks like this, where we have some J here that is going to have components JX and JY, and it's going to have that applied 7.5 kilonewton force. And then we have to look at our 2 force members. So Fi, being a 2 force member, is going to be at some angle here, and we're going to have force Fi. So starting with this, we can solve for what this angle might be between the bucket and this 2 force member. And what that is going to give us is it's going to be equal to the inverse tan of 0.42 over 1.44. You can just solve that using, the dimensions that were given here. It is a little bit confusing to be able to find all of them on here with the decimals and all that, but definitely valuable to be able to recognize the different distances and how to subtract or add them to get the angles that you're looking for. So what we're going to get from this is that is 81.2. So with that 81.2, we're going to solve the sum of the forces in the x direction, which is going to be Jx plus our force Fi, cosine of that angle, and set that equal to 0. From this, we can't really say anything quite yet, so let's do our sum of the forces in the y direction. It's going to be jy plus f1, or fi, excuse me, sine of some angle minus 7.5, and that's equal to 0. Can't solve anything still, so I'm going to do the moment about j to solve for what fi is. And that's because doing the moment about j, you'll be left with just one unknown contributing to that moment. So we're going to get negative 0.25 meters times 7.5 kilonewtons minus 0.4 meters times ffi sine of some angle. Plugging in what that angle is, we'll be able to solve for ffi here. That's going to be equal to negative 4.74 kilonewtons. And then plugging that back in, we should be able to find that fj is equal to 0.752, or excuse me, find that jx is equal to 0.752 I have kilonewtons, and jy is equal to 12.1875 kilonewtons. Already we've got the force in F1, but now we're going to want to go to another free body diagram to solve for the force in AB. So the one that I'm going to choose to go to next is this AJ one, because I already have some information. You know, I know what JX and JY are, as well as IF. So it'll be much easier to solve that one than it will be to solve the one that is at CH. So what that's going to look like is I'll have some free body diagram like this, with CX, CY, some force FI, some force AB, and some JX and JY. And once again, we're making sure that we're switching our direction of JX and JY because they were on our other free body diagram. So given this, we want to solve for what this angle is. We call this angle alpha. And the reason we want to do that is to find what AB is directionally, so that we can put it into our force equations. And what that's going to be is the inverse tan of 0.42 over 1.44, which is equal to 16.26 degrees. Once again, you should be able to solve that just by looking at, you know, what triangle we have here. That's 1.44, and up and down here you're going to take you're going to have to take like 0.64 minus this 0.22 to get 0.42. You know, being able to do that trigonometry is really helpful. And okay, with that angle, we can start our force equation. So the sum of the forces in the x direction is equal to negative cx minus jx minus fi, which we already know, cosine of theta, plus fab cosine of alpha. And that's all going to be equal to 0. Can't solve that yet, so we'll do the sum of the forces in the y direction is equal to cy minus jy minus fi sine of angle, or sine of theta, minus fab sine of alpha. And then Still can't solve that, of course, so we're going to find our moment about C. Because if we find our moment about C, then we have only the other unknown. Because remember, we know what both our force Fi is and Jx and Jy. If we were to solve about another point, we'd have too many unknowns because we don't know Cx or Cy. All right, so solving here, we'll get negative 0.25 meters times our force Fi cosine of theta plus 0.3 times our Fi sine of theta minus 1.93 meters times Jx plus 0.16 meters times Jy minus 0.1 meters times Fab sine of alpha minus 0.64 meters times Fab cosine of alpha. Something that's really important to keep in mind here is that when you're solving these moment equations or when you're writing them out, you want to make sure that you have both the x and y components for like your two force members, because Cy is not in line with where F1 begins, either in the x or y direction, which means that you have to include both the x and y components, and that's a mistake that I see happen a fair bit, is only including, your y components or only including your x components because you think they're in line when really they're not. All right, so this big long moment equation is going to be solved to give us Fab, and that's going to be negative 1.05 kilonewtons. Alrighty, so we can plug Fab back into our some of the forces in the x and y direction, but I believe it just said to determine the forces exerted in cylinders AB and Fi, so we have completed what the problem has asked of us. Okay, for problem 6, we are asked to determine the force P on the cable if the spring is compressed 0.025 meters when the mechanism is in the position shown. The spring constant, we are told, is 5 kilonewtons per meter. So, let's break down this problem into a few different free body diagrams. The first one that I want to start with is ACF. So we have our ACF, kind of like that. And what this is going to have is at our pin joints, like C, we're going to have our x and y components of force, and same at A. And at F, we are going to have some force downwards due to the spring. So we'll call it FSP for spring. And we are told the K constant, and we can solve for what this is using 500 newtons per meter multiplied by 0.025 meters, which is going to give us 125 newtons. So we know that force of the spring is 125 newtons downwards. I'll write that here. So then, what I want to get from this free body diagram is I want to find an expression that includes Cx and Cy, and that's because that is the member that is the pin that is connected to the rest of our structure. So what I'm going to get from here is that the sum of the forces, or sum of the moment about A, is equal to 0.2 meters times cy plus 0.2 meters times cx. And that's going to be minus 125 times, I believe, 200 plus 800, so just times 1 meter. And that's equal to 0. So that's all I really get from this free body diagram, but that enables me to go to member CDE and just know a little bit more about what is going on at C. So now moving on to CDE, we have this straight up and down member, which has some, oops, sorry. I solved X such that it was going in the opposite direction. Sorry about that. Just because I have CX going this way here and CY going downwards here. Flipping, your internal forces once again. And then I also know something about DB. And what that is that DB is a two-force member, which we can see because it has those matching forces in the X and Y direction at those pin joints. So here we're going to have force DB. And then, of course, we're going to have P at the top. So the very first thing that I'm going to do is solve for the moment about C. And what that's going to give me is I'm going to be able to solve for P in terms of FBD. And that's going to be FBD sine of 30 times 0.2 minus P times 0.35, and that's going to be equal to 0. Let's also put in some of the forces in the X direction and some of the forces in the Y direction. Okay, so you'll see now that we have 4 equations and 4 unknowns. So we have CY, where else do we have? We have CY, we have CX, we have FBD, and we have P. So now we have enough equations to substitute and solve for every variable. I'm not going to go through the process of substitution here just because it's very tedious, but I will tell you that you should come out with P being equal to 165 newtons. And we're only asked for P, so that's the only one that we really are aiming to solve for here. Okay, so last problem, we're on 7 now, and we're asked to determine the forces that act on B on the diagonal member, clearly indicating their direction. Very first thing that I notice is that BD is a two-force member, so really we're only looking for some tension BD that acts on that two-force member BD. So I would solve this using just one free body diagram here that has our 90 degrees, or excuse me, 90 pounds at the top, our CX and CY. and our tension TBD. So this free body diagram is the only one we need to solve really, and we're just solving for TBD, which means that we can just solve for the moment about C. And that's going to be equal to 12 inches times 90 pounds minus 4.5 inches times TBD cosine of some angle. And that angle is this angle right here. The way we find that angle is by taking the inverse tan of 4.5 over 6, which you can get from the diagram very easily. And what that's going to be equal to is 36.8 degrees. Alrighty. Plugging that in, we're going to get here that TBD is equal to 300 pounds. And that's in tension. You really do not have to solve for some of the forces in X or Y because we don't need to know what CX and CY is. We just need to know that TBD is 300 pounds and it is in tension, which you can get either just by analyzing the appearance of our free body diagram or by solving it out and getting a positive number. What I mean by your intuition telling you that it has to be in tension is that your negative horizontal force is going to cause BD to be in tension. You know, since you've got your 90 pounds going this way, BD must be pulling the opposite way, putting it in tension. So you could solve it that way, but I always think that solving it mathematically and getting a positive number is the best check. Moving on to 7b, we have a system of bars that is loaded with 50-pound weight on the horizontal bar AB, and it's held in place by pin joints ADF and a horizontal linear spring at E. I'm noticing, you know, ECD is vertical, slots B and C are frictionless, you know, just little details. And then what we're actually determining is the force exerted by the spring on the vertical member and the forces experienced on the diagonal member at F. So I'm going to break this up into a few different free body diagrams, but first I'm going to start with that horizontal member AB. It is the only one that I'm noticing right now that is only going to have 3 unknowns because that weight is known. It's 50 pounds. So let's draw that out. We have our AX, AY, our weight pointed downwards, and our force B. Remember that at slots like this, since you can move in this diagonal direction, you're not going to have any component of reaction force going in that direction, meaning that your only reaction force is going to be pointing exactly perpendicular to the slot. So that's why I have my FB going diagonally there. And leave it in terms of FB rather than some X and Y component, because when you put it in terms of an X and Y component, all you're really doing is making more variables for yourself, which is going to make it impossible to actually solve this free body diagram. So solving this one, I'm going to start out with my moment equation about A in order to find what FB is. And what that's going to give me is negative 8 inches times the weight plus 16 inches times FB sine of this angle. That angle is going to be 45 degrees, which we can just tell by looking at our free body diagram here. So that angle is 45 degrees. You can see like here to here is 4, And here to here is also going to be 4. So we get a 45-degree angle. A probably easier way to look at it is by just doing this entire vertical distance here and the entire horizontal distance here. It's going to be 20 and 20, so we know that our angle is going to be 45 degrees. Okay. Now, plugging that 45 degrees in, we're going to get our force B is equal to 35.4 pounds. And then we can plug this into some of the forces in the x equation. AX plus FB cosine of some angle is equal to 0, giving us AX is equal to negative 25 pounds. And then some of the forces in the y direction is AY minus W plus FB sine of 45, which is equal to 0. And this all will give us that AY is equal to 25 pounds. So now we're going to move on to our next equation, or our next free body diagram, which I'm going to do BCF, which is that diagonal one. So here, let me just reduce the size of this really quick. Here we're going to have some free body diagram that looks like this with some CX. Once again, since that's a slot, we only have a perpendicular component that is perpendicular to the slot's direction. And then FAB up here, or FB, with this angle theta still. And then we have our forces Fx and Fy. So once again, we only have 3 unknowns, CX, Fx, and Fy. So first, I'm going to solve our moment equation about F. I'll do that down here. Some of the moment about F is going to give us negative 10 inches times x plus 20 inches times FB cosine of some angle plus 20 FB sine of that angle, and that angle being 45. This will allow us to solve for CX, and that is going to be 100. Yeah, that is going to be 100. Alrighty, so then we're going to solve our other 2 equations. I'm going to reduce the size of this again. I'm just really running out of space here. But we're going to have that the sum of forces in the x direction is equal to Cx plus Fx minus FB cosine of 45. And then the sum of forces in the y direction is equal to Fy minus FB sine of 45 degrees, which is equal to 0. And from this, we're going to get that Fx is equal to negative 75 pounds, and Fy is equal to 25 pounds. So, they are asking for the force exerted by the spring on the vertical member and the forces experienced on the diagonal member at F. So we want to write here specifically what they are on member F. I would write them in Cartesian coordinates just to really show that you know the actual directionality of all of the different forces. So what that's going to look like is I'm going to have my force C be equal to 100 I hat, because I know that C is actually going in this direction. My force of F is going to be equal to negative 75 I hat, and that's because I drew this in the wrong direction, because you can see I got a negative value from it from my sum of the forces in the X equation. So it's going to be negative 75 I hat plus 25 I hat. I drew this one correctly. And then my force B is going to be equal to 25 I hat plus 25 J hat. And that's because, see that we have our two components this way. And based on how we solved them in the initial free body diagram, we then have to carry that over and find that we drew both of these in the opposite direction of what the actual force is, which is both positive. All right, so that is our final answer. You're not required to inspect DCE for the solution, but if you want to, you can do that and solve for what EX is, but this is all that you really need. Good luck on your exams.